Okay, so kule video ngizoyenza le question le ethi a steel ball of mass 0.5 kg is suspended from a string of negligible mass. It is released from rest at point A as shown in the sketch below, and as it passes through point B, which is 0.6 meters above the ground, the magnitude of its velocity is 3 meters per second. And then we are told to ignore the effects of friction, right? So decide ukuthi ngifake le question le in. It's not strictly related to momentum, but then if you familiar nama work energy principles from grade 10, principles of conservation of mechanical energy, you should be able to do this question, right? So isathu sokuthi ngifake is I don't want you guys to be caught off guard maso ivela exam. So it might be out of your syllabus, but then for completeness sake we decide ukuthi siyenze, and then if it happens to show up and then ukuthi ukhona nawo uyiphendula, right? So bathi ku 4.1, write down the principle of conservation of mechanical energy in words. So this one is kind of similar to the principle of conservation of linear momentum. So you would say in a closed system the total mechanical energy is conserved, right? So it's very similar to the principle of conservation of linear momentum. So the principle of conservation of linear momentum, of mechanical energy states that the principle of conservation of mechanical energy states that in a closed system the total mechanical energy is conserved or remains constant. It's conserved or remains constant, right? So yeah, that's the principle of conservation of mechanical energy. You might not be able to see because the lighting is very bad. So yeah, reflection light maybe in a seat somewhere, but then the principle of conservation of mechanical energy states that in a closed system the total mechanical energy is conserved. Okay, so 4.2, and then 4.2, but to calculate the mechanical energy of the steel ball at point B. Right now, if you go to a formula sheet yako, kila wangasendile lapha groupini, you'll see ukuthi akhona ama formulas where work, energy and power. So my formula so asebenzisa ilawo, right? So at point B we want to calculate the mechanical energy at point B. So its mechanical energy, it will be equal to the kinetic energy at point B plus the gravitational potential energy at point B. So EK is kinetic energy, EP is the gravitational potential energy. Right? Remember what the kinetic energy is an energy which has to do with an object's motion. So every moving object has a kinetic energy, right? So a kinetic energy of a stationary object is 0 joules because that object has no velocity. The kinetic energy depends on an object's mass and its velocity, and then the gravitational potential energy is an energy that has to do with an object's position relative to the surface of the earth, right? So if gravitational potential energy is influenced by an object's mass and its height above the surface, or its height above the ground. So for kinetic energy, we'll have 1 over 2 mv squared, right? So it depends on an object's mass and its velocity. And then for potential energy, we'll have mgh, where g is the gravitational acceleration, which is 9.8 meters per second squared, right? And then h is the height above the surface. So at point B, we are so this steel ball has a mass of 0.5 kg, and then at point B we are told its velocity is 3 meters per second. So here I'll substitute 3, right? And then at point B, the mass of the object is still 0.5, and then the gravitational acceleration is like always 9.8 meters per second squared. And then we are told at point B, the steel ball is 0.6 meters above the ground. So they will substitute 0.6, right? So let me grab my calculator and then calculate and see what's the answer. So 1 over 2 times 1 over 2 times 3 squared plus 0.5 times 9.8 times 0.6, right? And see, the answer is 5.19, and the unit for energy is joules, right? So it's 5.19 joules, right? And then we move on to question 4.3, right? So, but as the steel ball swings through its lowest point at C, it collides with the stationary crate of mass 0.1 kg immediately after the collision, right? And then the crate moves at a velocity of it moves at a velocity of 3.5 meters per second to the right. And they want us to calculate the velocity of the steel ball immediately after the collision, right? So here you might be tempted to use the principle of conservation of linear momentum, but then we would use the principle of conservation of mechanical energy. So you'll see how we apply this principle of conservation of mechanical energy is very similar to how we apply the principle of conservation of linear momentum. So applying this principle will say the total mechanical energy at point B will be equals to the total mechanical energy at point C. The total mechanical energy at point C, right? So this is very similar to the principle of conservation of linear momentum. So yakhumbula principle of conservation of linear momentum, the total linear momentum before collision is equals to the total linear momentum after collision. In this case, the total mechanical energy at point B is equals to the total mechanical energy at point C. So now, the way we proceed is also very similar to how we do this if it was a linear momentum question. So at point B we have kinetic energy and gravitational potential energy, right, at point B. And then at point C we also have kinetic energy and gravitational potential energy, right? And then at point B we can calculate so this is the mechanical energy at point B. It's the one which we calculated in 4.2, because at point B we'll still have the same ball of 0.5 kg, and then its velocity will be 3 meters per second, and then the height above the ground at point B is 0.6, and then the mass will still be 0.5. So the total mechanical energy at point B will be 5.19 joules. So here I'll write 5.19, and then at point C I want to calculate the velocity of the ball at point C. So at point C, I have kinetic energy as 1 over 2 mv squared, and then it's mv squared plus the gravitational potential energy at point C is still mgh, right? So now I want to calculate the velocity of the steel ball at point C, right? So this is 5.19, it's equals to 1 over 2 times 0.5, the mass of the object, and v squared, and then say plus 0.5, the mass of the object, times 9.8, the gravitational acceleration, and then at point C, this ball is at its lowest point. So there we can say the height above the ground is 0, right? So we will have 0, this will be 0, this entire thing will be 0, and then we'll have our velocity v squared to be equals to 1 over 2 times 1 over 2 is 1 over 4, so 5.19 divided by 0.25, right? And then we'll have to take the square root of this to get our velocity, right? So let me grab my calculator and see. So it's the square root of 5.19 divided by 0.25, and then the velocity of the steel ball at point C is 4.56 meters per second. Okay, and then you are done with that question. So the way you apply a principle of conservation of mechanical energy is very similar to how you'd apply a principle of conservation of linear momentum. So yeah, next time if we want a question or a panic, just know what you will have to use the correct formulas, kinetic energy and potential energy. And then yeah, we are done. Okay, we'll move on to the next question just now.